So the next talk is Shahab, you're on with
Yes, I am.
okay, it's my co-author Shahab and I, and we're talking about a die-to-die interface comparison we first did in the ODSA first did in 2019, and we're carrying it forward and giving you the results of the 2020 update. Okay, sorry. Okay, so um, the big changes we've made this in the 2020 version compared to the 2019 version are thanks to a group effort and thanks to Shahab's some solid work from Shahab, we are now have very precise definitions for all the parameters in this die-to-die comparison. And at a top level, what we're trying to do is come up with an objective metric by which you can compare die-to-die files. What we're not trying to do is to sort of pass judgment, and we're leaving that judgment up to the reader or to the reader who's using the data. But what we are trying to do is to get one uniform set of metrics by which a file can be evaluated and get the community to agree on the definition of those metrics. Compared to 2019, we also dropped some categories, right? So just to sort of put this in context, this is a part of the die-to-die interface definition effort, and we're trying to sort of give you a easy method to evaluate a range of PHY technologies. Roughly, that's where we're at. And if you're online and if you have any questions, please feel free to interrupt us at any time. You just heard the discussion that Alan prompted, and it was a very nice discussion. So if you'd like to jump in on the Zoom link or type a question on the message board to the right, please go ahead and do so. A whole bunch of people participate in this. In fact, one of the most sort of endearing things about this was that, like last year, it was a good community effort. I think I really wanted to do a shout out to Toru and Toru for being a good representative for the PCIe for giving us benchmark reference data on PCIe. We had a whole bunch of other people who helped out on at different stages. One of the big things was that we pretty much anybody who had a PHY was gracious enough to share their data. And we also had quite a few people join the effort after late after the definition of many of the terms. The reason I bring this up is at the end of the talk, we'd like to, Shahab will go over this in more detail, but we'd like to have you also, if you have a die-to-die file and you want to add it to the compendium, that's definitely not too late. You're more than welcome to do so. So what we're here to do in this talk is really, as far as the whole ODSA goes, is really to talk about die-to-die files. And in case it's a bit late since we're halfway through the second session of the ODSA track, but just so we're all aligned, really we're talking about the thing in the thing in purple or pink in this. Really the physical layer and the electrical connection between two die. On some devices you may have an interposer, and some devices you may not have an interposer, but the working theory is you need one of these if you're going to do a chiplet-based design, and you're going to put multiple chiplets into a package. And every pair of chiplets that need to talk to one another are going to be linked by a die-to-die file. So in terms of history, really what we started off was we did this last year, led by Greg Taylor from Ziegler. And we published it at Hot Interconnects in 2019. And really, at that time, we had roughly the same aim as we have this year, which is to give you users a common framework in which you can evaluate die-to-die files. We're updating for 2020, actually prompted by an ask from Taufik at Microsoft. It was like, okay, let's go off and do this again. What's new in this edition is really a much tighter focus on the metrics we care about as we've learned more about the problem definition. And as I said, very precise definitions, and we had more vendors participating with their die-to-die files in this. In terms of how we did it, we pretty much had an open call for anybody who's interested to join in. It's still not too late for you to add your die-to-die file. I do want to say specifically that Intel's AIB file, the information we have is from public sources. It isn't provided by Intel. All the other files were pretty much provided by either the work stream working on the working on the file or the vendor developing the file if it's a proprietary design. And we used last year's spreadsheet as a starting point. The meetings were fairly exciting because seems to be a topic everyone cares rather deeply about. So at a top level, last year, Greg split the metrics into four broad buckets. And I think for the most part, Shab, it's fair to say we've retained these metrics and maybe sort of played around with the internal definitions. So the first thing we said was, how much does it cost to make it? If you're going to add this data file, how much is it going to cost you to make the file? It was roughly a measure of area and what manufacturing, excuse me, what substrate technology you needed for this. The second we kind of figured out was what's it going to cost you to operate it? Is it in terms of power? If it's yeah, how much power performance are you getting? And there's a fairly well established figure of merit that we put together that we borrowed. It was originally from DARPA, and we essentially sort of borrowed that and retained that. This year, on top of the figure of merit, we created a second figure of merit, which also sort of seeks to recognize that some fires are optimized for longer distances, longer reach. Um, Shahab here is still not a huge fan of the second metric, but we're working on him. And the second thing is we paid a lot of attention to latency, right? That's the operating cost bucket. The third bucket we sort of put a lot of energy into is the cost and complexity of design. So if you have tons of wires moving between chips, then does that basically make design on an organic substrate much more complex? For example, how much routing freedom do you have? What orientation dependencies do you have, etc. How many process nodes do you support? Because if the more process nodes you support, the friendlier you are to heterogeneous integration. Then how complex or easy is it to get the IP? If it's and finally, what are the costs of producing and testing this once you manufacture this? So roughly, that's kind of the design impact. And there's an argument to be made for production and test and assembly to be under operating costs as well. And then the fourth bucket we have is product integration. As you can see, we sort of replaced last year's categories with two new big buckets: product integration, or we've kind of largely renamed them more than replacing them. And basically, the whole idea is really what kind of business risk are you taking with this? Can you get the interface? Do you have to pay a licensing fee any royalty fee for the technology itself? What kind of porting complexity do you get when you try to move the IP from one process node to another, etc. And the one thing added, that specific add-on we have for 2020 is that where possible, if you claim to be proprietary, we want this to be a clear link to an existing open standard that somebody can point to and retrieve. That's a one big ask. Excuse me. So at this point, I'm going to stop sharing my screen and hand it over to Shahab, and he's going to take this over. Excuse me while I stop sharing my screen. All right.
Okay, do you see my screen, Bapi?
Yes, we do.
Okay, thank you. Okay, hi everyone. This is Shahab Ardalan. As Bapi mentioned, we have number of files with the different standard available for die-to-die interface. Actually, this makes the job of the chip architecture so difficult to pick one for their products. At ODSA, we try to establish a platform where we can actually capture different features and performance metrics of the existing files. In next couple of slides, I'm going over the platform and present some parameters that we capture for each of this interface. For example, if I can be unidirectional or bidirectional, simplex or duplex. And that actually brings a couple of challenge to us when we want to compare all them under one umbrella. For example, if we are dealing with the unidirectional phi, which has only one TX and RX, and compare the same number in terms of the power and area for a bidirectional link, which has a TX and RX, we have to do some adjustment to be fair in the comparison. In basically in the we decided actually to map basically everything based on a unidirectional simplex link. For example, if we are dealing with the duplex and it's a basically bidirectional link, if we are trying to report half of the area for that specific phi, to be actually fair comparison between the unidirectional link that they only have a TX or RX. That's something that we also defined this year. And also we wanted to see what is the minimum unit of that specific phi. For example, I picked the example of Bo because it's part of the OCP. In Bo, the minimum unit that we can have is basically 16 lane of the data with the 2 clock and 2 auxiliary line. And this is what we define as a unit. And we also report some number and performance based on a unit. Again, in the contrast, when we are talking about the XSR 112 gig, the unit for that one is going to be 2 data, which is differential link, and there is no clock and there is no auxiliary. That's actually the comparison that we can make and find out basically the beachfront and all the other parameters that we want to extract. Further details in terms of basically a link and number of wires. We divided actually the number of wires in a couple of different categories. For example, we captured the number of data that is actually needed for make the communication between the two units. Again, remember units are simplex and unidirectional. And also we captured the number of clock wires that we need, or for example, in some of the cases which the phi standard is not clock forwarding, it's 0. And some of the standards, they require some other wires, which we call it auxiliary or FEC or some other things. This is actually, we capture again all this data to create that unit of the TX and RX that we are talking about. Based on all this information, I think we come up with a couple of performance metrics. One of them was actually, again, we wanted to see how much is on the basically one unit cell. We defined a unit bandwidth in each direction, which was basically gigabit per second in terms of the unit. For example, in Bo, because we have a 16 line and it's actually 5 gigabit per second, it becomes 80 gigabit per second per unit. Compared to the XSR, which is 112, and again, it's a differential. We have to have a 2-wire divide by 2, which has become 112 gigabit per second in terms of comparison of the unit that we need. And from the other side, also, we wanted to know how much is the power for the unit, which we include actually TX and RX and all the clocking. If you look at this basically diagram that we have here, we decide actually to capture everything after FEC from the TX side all the way to the RX before FEC, basically including serialization, deserialization, and RX and TX unit that we have. I see already a typo here. This should be a TX. We didn't fix it. This is basically what we reported as a power for now. Another parameters that we wanted to capture, and as Bobby mentioned, that was kind of hard to get everybody agrees on it, was the latency basically and bit error rate. We know there are some standards out there that because of the nature of the signaling and communication scheme that they are picking, they may require actually the FEC or they may not require the FEC. That's why we had the hard time to defining basically different type of the latency and bit error rate. What we did was basically we decided actually to assume the FEC is going to be outside the serializer, and is going to happen between 1 gigahertz core logic and a serializer. We know that this could actually happen outside or some other places at the top level in terms of the architecture implementation, but we decided actually to report everything in this uniform fashion. First of all, we're going to report latency without FEC from the beginning of the serializer to the end of the serializer, assuming that the input to the serializer is a fix at the 1 gigahertz core clock. That's what number that we recover, we report as a latency without FEC. At the
Just a
same
quick
time,
clarification, Suresh. Equalization and DFE, are they considered part of the FEC or are they considered in the serial in?
they consider as a part of unit RX and TX.
Okay, thank you.
Yeah. And then bit error rate without FEC is actually again measured from the beginning of the serializer to the end of the deserializer. Since we know some of this bit error rate that we are measuring may not be enough for application, we decided to fix the bit error rate, which is 1 e to the power of minus 15, oh sorry, 10 to the power minus 15 or 1e minus 15. And we measure latency based on this required bit error rate. Then this is actually the judgment for the file provider to see if they need effect to achieve this kind of bit error rate or not. Sometimes, for example, this could be exactly same as the top one if you don't need, or if you need, then you're gonna add basically the fake latency to it as well. Again, we one more time I should emphasize, we decided to actually have the 1 GHz core clock here to make it so uniform and simple for everyone. In terms of area and reach, I think again one more time, we decided actually to report the unit TX as a beachfront, or the number that we need to calculate the bandwidth density depends on the area of the edge chip. And if we are reporting a total physical area, which is the RX and TX together, this is going to be the area that we're going to report all together. Some of the standards that we see actually, they start actually stacking number of units to the actually going to the inside the chip, not getting actually grow to the edge of the chip. It's going to the inside the chip. This actually cause couple of issues. It has to be actually in terms of the signal integrity maintainable in terms of the link budget, and also how much loss do we have. Therefore, we define actually something as we call maximum stackable unit, and that's actually defined by each standard. Some standards they claim 5, 6, and it's also important to see what kind of package do we need for those kind of standards. And also we have to see what is the maximum distance between TX and RX unit in this case that we can actually compensate and have a correct link without the error. That actually gives us the maximum distance between RX and TX in the link. Some of the standards, for example, they decide actually to have the first TX connected to the first RX and the last TX to the last RX. Some actually prefer go to the first to second and the other one to the first, basically to keep the distance the same, or in the other scenario you do have the best reach and max reach. This is a comparison table based on all this information that we provided, although the real Excel sheet is so big, but we were actually able to cover 15 or 16 different existing standard or PHY available in the market. You see there are actually mainly in 2-3 groups. I can say there half of them are focused on the micro bump area, something like between 40 to 55, and there are the rest of them which are in their 130 micrometer pump pitch. And Bo by itself actually covers, and I think AQ also, they're gonna be on the basically both sides, depends on the flavor that you're gonna pick, either on the micro bump or on 130 micro pitch. This actually defines you're gonna go basically on the silicon interposer or laminate organic interposer. Then we do have a power efficiency, which is the picojoule per bit, and edge density is important for us. How many terabit per second we can get per millimeter of the edge chip. That was another factor that we defined. And area density is also terabit per second per millimeter square. That was basically only the edge. Now this is actually the total area that PHY is gonna actually take for each terabit per second communication. We defined actually 2 different FOM. The first FOM is edge density per power efficiency, which is terabit per second per millimeter per picojoule per bit. The larger number is better. We do see a variation from very small number to the large number, something like 7 and 6. Depends, I think, on the approach that we are taking. For example, if we are going to the more parallel silicon interposer, you see higher number compared to the other one, which is at the micro bump space and not parallel, which could actually be in the middle range or older version at the bottom of the chip. Also, it was important for us to add another level to this FOM, which was actually, we saw that this power dissipation and the edge density, they don't have how much compensation of the channel loss do we have. Basically, there is no information for how much we can reach. Therefore, we introduced another FOM, which is the picojoule per bit per millimeter of the reach. And again, that's actually smaller is better, and we see most of the people are in the order of the basically 0.01 FOM. as a targeted value. Again, what one I have to mention that most of this number we captured it. We are not here to, we never basically validate this number. Some of them are based on the projection. And feel free to send us your link if you want to be part of this table for next year. What we find out was basically all the power is important. I think we do see a lot of picojoule per bit, but this is again, these are some projected number based on a 7 nanometer, and except some variation if you are changing the process and also the condition, voltage and temperature. As I mentioned, defining latency was kind of hard. I think we spent a lot of time on it to get everybody's agree on the terms and definition. As I said, our target right now for for latency is when we get the bit error rate of the 1 to the power of minus 15, 10 to the power of minus 15. We have basically a workable solution and environment right now to capture all the parameters that we need and plug into it and get to the meaningful comparison with the others. If you do have a phi, or if you are interested about the phi and you don't see it in our table, feel free to contact me or Bobby. Then we're going to add it to our table and you see basically how it's going to perform compared to the others. Bobby?
Yep, and obviously you're free to just use this work even without sharing the results. Shab, since we have a couple of minutes, do you want to just walk through the spreadsheet so somebody can see how they can add their phi if they so desire?
Sure. Give me 1 second. I have to bring it to the.
If anybody has any questions, please feel free to do what Alan did. Hopefully, Alan has one more question somewhere in his back pocket for us.
Did you guys see my screen?
Yes, we do.
Yeah, this is basically all the information that we captured so far. I mean, you see that this every row has a different parameters. Some of them that we didn't mention, for example, IO swing, how much is the swing, how much is the bump spacing. All this data, that the green one that you see, this is the information that we need from the vendor or provider of that link. Some part of it is actually depend on the architecture. It's a DDR, QDR, or it's a clock forwarding or not, termination, not terminated. A lot of implementation information is also captured here. And then the point that it's not basically green, these are basically the data that we calculated. It's basically the figure of merit, power, density, and those kind of thing in two categories. One is in general, one is actually if you really want to target 1 terabit per second, how much you have to pay for it. And the link to their open standard is also available. I think the links that we tried to cover, you can see from AIB all the way OpenHBI, BO, AQ Link, Analog X Can Do, Alpha Wave, Sci5. Everyone, I think, are when they provide their numbers, we try to include it here.
Hey Shahab, Ravi
Yes.
has a question. Have
Sure.
we considered direct drive? What's
The,
direct drive?
yes, that was my question too.
Ravi, if you're on, would you mind just typing it in, or I think you can join the Zoom link too, if you can tell us what direct drive is. Oh, that's funny. I think this might be um, okay. It's not clear that the platform seems to be stale. The question says it's an hour ago, but so okay, we'll figure it out.
Okay.
Okay. Any other questions online?
We do have 2 more minutes if anybody has a question.
I guess just one quick one then. Seeing Baffy put me up to it.
That's right, Alan. Thank you.
How do we decide what are the most important figures of merit to use? I mean, there's a lot of choices, and I had a go. But yeah, I guess that's an interesting question, right? Is power the big
So
figure, or terabits per second per millimeter, or latency, or some
I
mix?
think it really depends on the application that you're gonna pick and
there you go.
also the cost that you want to pay. I think if you ask me, I think the big question is how do you want to make actually the integration? It's the bomb pitch. I think that can actually define immediately in the two different categories that you go to the silicon interposer or organic interposer type of phi. And after that, again, I think it becomes to again couple of other things. For example, you do need latency or you don't need latency, or do you want to be actually unidirectional, or your link is fully symmetric, or it's just basically 90% of the time it's in one direction. There are, I think, more on the architecture side rather than just picking one and say, oh, this is the best compared to the others.
Thanks. Yeah.
So yeah, hey, Ravi is online. Ravi, fire away.
Direct drive is actually a next generation of interconnect interface, especially between optical and electrical switches next to XSR. This is for 200 gig application.
Correct me, Ravi, but if I know, I think at least I haven't seen any release the standard on that, and we don't. I never heard of anybody who has it. If you know anyone that they are willing to share the information about the XSR 200 gig, we will be more than happy to add to it. But I assume it's going to be a next version of the 112 gig.
Thanks.
But I'm not sure. I think there was a discussion that it could be different than PAM4, but I don't know what happened.
So actually, Ravi, if you look at the spreadsheet, right, one of the good things we have is that every column has a name associated with it, who's essentially the owner. So if there's some, Toru was gracious enough to do PCIe, and then Shahab did AIB himself. So from public information. So if you have someone here, we'd love to have them added onto this list.
So let me take a look at it, Bapi, the list, and then I heard that company is part of this discussion. But let me reach out to the person and see if they feel comfortable adding it.
Sounds good. Okay, that'll be perfect.
Yeah, thank you very much.
And Alan, to your point, what last year, and I don't see any major reason for the thinking to change. It felt like your choice of a phi would kind of be defined by your use case, what you were targeting in the design space. And I think we've lost Alan, so we're good there. Okay, any other questions online?
Bobby, this is JP. Do you have a time for one more question?
Of course.
Yeah, so when this is a very interesting study comparison of different phi technologies. Did you take into account of that the back end of the phi, how many parallel lanes are coming into the phi, and how the SerDes architecture is implemented, or is only the final driver part, the metrics you presented?
Bobby, do you want to comment or should I?
No, go for it, please.
If you notice, we decided actually to fix that as a 1 gigabit per second. I don't know if you catch that or not. Maybe I should explain it more. But we decided that the data that we are getting is going to be 1 gigabit per second. The reason that we got 1 gigabit per second, I think this is the basically domain that people can do place and route and do digitally.
Mm-hmm.
So once you know it's a gig, what happens is you know what the ratio is between the internal clock logic and your wire speed, and you know exactly what kind of fan out you need. So then you get a sense of how many wires you need for, let's say, a 64-bit bus or whatever it is that you're dealing with on the inside.
Which is happen at the serializer and deserializer.
So this is done to normalize across different phi implementation, is it?
Exactly.
Yeah.
Okay. Very nice. Yeah.
It turned out to be a major change from 2019. Was this all of us agreeing on 1 gigahertz as a normalizing factor?
Okay. Thank you.
For example, in case of, again, AIB to just, Bo to just add to it, Bo is going to be on the 5 gig, then you need to have a basically 5 lane. The serializer at the inside the Bo needs to take care of the basically that 1 gig to 5 gig conversion. Mm-hmm. And in case of the XSR, which is 112 gig, they have to consider 112 wire coming in and convert it to 1.
112, okay. Yeah, interesting.